Um, Work and energy. So a bit of an overview of the next two chapters. Now I know you've heard that energy is conserved. Energy is, I mean, what is it? It's one of those questions where the kid keeps asking why, like, but at some point, the answer, there's no why. It's just the way it is. Things that are a little bit more easy to even see in that regard are something like gravity, for example. Where does gravity come from? Well, there's no origin, but when mass accumulates, we have gravity. Why? Well, because that's just the way it is. Or why is gravity attractive? Why isn't it repulsive? There's no reason other than we look out in the universe and we see that's attractive. So the theory starts there. You start with that empirical observation, Newton did, looked at a couple other things, put an equation together for the equation of gravity. G mm over r squared. Same thing with the charge. Coulomb. Oh, well, we haven't got this is mechanics, so nothing. Scratch that. So yeah, and we haven't defined that yet, but we'll do that later on in the semester. But still, you understand gravity from Newton's second law point of view, and so energy. What quantum mechanics speculates is that energy is if you ask what is energy, the question answers itself. Energy is energy. There's nothing other that builds up, that works up, that is a building block that creates energy. In fact, it's the other way around. Everything that you see in the universe, the fundamental, if you keep breaking it down, the fundamental basic unit of the smallest component or aspect of that thing that you can imagine is energy. So there's nothing that energy breaks down into other than more energy. So it's hard to describe it in the context of something else because there is nothing else. And when you start to get to quantum mechanics and you start to kind of look at the implications, basically people start making comments like everything is energy. And when they mean everything is energy, they literally mean everything. The current theory, and I think I might have mentioned it, is string theory. And you can come at it from a different point of view, but basically, in a nutshell, I might have mentioned in this class before that we think that when you start to break down an atom, it breaks down into protons, neutrons, electrons, but the protons and neutrons actually break down into smaller particles, which are called elementary particles. Things like bosons, muons, heptons. These things also break down into smaller particles called subatomic particles. And at some point, someone speculated that if you just keep going, what seems to be matter or you know discrete tangible objects actually break down into different types of energy. What I like to use the word corpuscles of vibrating energy that are very, very small. The lay term, or the not lay term, but the kind of popular term, or one popular term, are strings. And where that comes from is if you think about a stringed instrument like my guitar over here, you string up a chord between 2 points and 2 nodes, and the object, if you pluck it, it will vibrate. But depending on certain properties of the thing, the thickness of the density of the string, really, the length of the string, um, and I guess how tight it's wound. When you pluck it, it vibrates, but it vibrates at and the only characteristic, the basic characteristic that we use to describe the vibration is frequency. Now you know what frequency is. Oh, wait a minute. I just realized I have to do more problems with centripetal force. So we aren't quite finished with that section. That's what I wanted to do today before I got into this. Okay, so I'm going to finish these thoughts, and then I'm going to go back and we have to take a look at centripetal force problems a little bit more. It's not much. There's not much theory because we already described centripetal acceleration. But remember, I told you when we did that, I wanted to wait to do more comprehensive problems because we need to have the force. So that's a little bit of a lecture. That's about 45 minutes and then working a couple of problems. So we got to spend about an hour on that. So I'm sorry. I forgot that we hadn't done that. But let me just finish this introduction, this somewhat, well, I have to cut it short, but somewhat introduction that I'll come back to. And that's what I mean. That's the kind of stuff that's been going on all the day. I'm very distracted and I couldn't figure it out, but I think it's the war. Strings. So we defined period and frequency when we did centripetal acceleration. But we actually have to define centripetal force in order to kind of continue with and be more comprehensive and work the problems. But at least you know what frequency is. Frequency is the number of cycles, number of vibrations per unit time. And the period is the inverse of that, is the time of one cycle. But frequency actually, even though we talk about period a lot, really frequency is more fundamental, I think. And meaning it's, when we get to quantum mechanics, basically, if you know the frequency, the direct, the energy, well, in a string like this object here, like this string here. Now I have it on a guitar and we just use it to make sound, but you could turn it into a weapon, for example, to get the energy that's inherent in that string out by making a bow and arrow. In that case, you don't necessarily use a vibration, you just use half a cycle, because by pulling it back and attaching something to it, pulling it back gives it potential energy, and then you convert that potential energy into kinetic as it goes back to equilibrium. And so it's a way of kind of harnessing or taking the energy that's inherent in the potential vibration of the string out and using it for something. And of course, that's using it for a weapon, but we can use it for other things. We use vibration for other things. Another way that you see the energy in vibration is sound. You know, the opera singer sings a very high note. That's vibration. And you're making your eardrums vibrate at a certain frequency, which we have that vibration in your eardrum is converted to an electrical impulse, which is read by your brain as a particular frequency of sound. But there's energy in that as well, which you can see when the opera singer sings and causes resonance in a glass and causes it to break. Now, that's a little bit more common. We'll talk about resonance a little bit later on in next semester. We don't do so much of that here, but what's happening there, just as I mentioned, described to you, I think I've mentioned several times that whenever because everything is energy, and because what distinguishes the energy from one object to another is how that energy is vibrating. And it can be, and it's such a fundamental principle, this thing about vibration, that some things can vibrate at frequencies that are so different than other objects' vibration, then you can't even see them. And not only that, you couldn't even feel them. Like in the extreme aspect of, well, I think I mentioned it the other day. I don't know if it's this class, but there's a movie out now that's pretty popular, The Flash. And one thing that the Flash can do is walk through walls. But what they've dramatized in the movie is that he starts to, because he can move real fast, right? Linearly translatory or translational motion. But vibrational motion is just translational motion where you're changing directions very fast. And you just go back and forth. That's vibration. So because he's also, very fast, he can also vibrate with extremely high frequencies that are kind of unrealistic, in what we think in regular terms. So that they're illustrating something in that that's fundamentally true, at least theoretically, that you can have vibration. So you know how this is an analogy that's something you can relate to. Oh my God. um, you know how you can make a dog whistle where the dog whistle is so high that, well, the it makes a sound that's the frequency is so high that you can't hear it. Well, does that mean the sound isn't there? Well, no, it's there. It's just that your eardrum is not sensitive enough to pick it up. Now, what does that mean, sensitive? It means that mechanical devices are created in such a way where there's only a specific range of frequencies that it can have, just mechanically speaking. Because of the physical way it's made, it can't vibrate enough, or slow enough or fast enough to pick up certain vibrations. In the case of high frequency, the vibration is very fast. So when it comes across our eardrum, basically nothing happens. Or, yeah, it's just our eardrum can't respond to it. So it's like the sound isn't there. Now, because we are having intuition for that, even if you didn't know that exactly, me explaining it to you right now and hearing it for the first time, you kind of probably have an understanding of what I'm talking about, just because it's in the nature of your experience, even if it's subconscious experience that you never really thought about. What seems counterintuitive to us is that someone would be able to walk through a wall. But if you understand that on what we call the Planck scale, there is no matter. Everything is just energy vibrating at a different frequency. Taking the analogy from what I just said with sound, you can also say the same thing about matter. That right now our bodies exist as matter, what seems to be matter. But what it really is energy that has slowed down its vibration by combining into subatomic particles, subatomic particles, then subatomic particles, then atoms, then molecules, then you know compounds like and then our bodies. It's just energy that has, and this is one point of view, one perspective, energy that has, when it combines, it starts to slow down in such a way that now we could define an overall frequency for whatever that object is, like our body. Now, I know this is going to start to sound a little bit Eastern, but when you start to talk about Eastern philosophy and meditation, and people talk about your energy and your vibe and the whole universal all that stuff, if you think about it, it's really saying the same thing from a very different point of view, because the is the sound of the vibration, and we actually physically do have vibration, right? And we can. It's not unreasonable that, well, let's just let it write it. Just say that point that that's the vibration that those Eastern philosophers are talking about, and it's true. Like everything has a fundamental vibration. And if it's built up from energy, it will change. Like when two things, like when hot and cold come together, they, they share energy, and they come to a medium temperature. The hot object lowers its temperature. The cold object, um, increases its temperature, and you have some superposition of the two temperatures. Well, frequencies superpose as well. We see that with sound, right? When we have one string and we pluck it, it's a certain frequency of sound that's vibrating in the air. You have another thing, frequency, but if you pluck them together, it combines, it superposes and makes one sound that's a combination of those two. Well, matter does the same thing. So whatever physical physical quantity you have, if you could figure out a way to determine its overall vibration, essentially that would be its overall frequency. That would just be a superposition of all the individual particles and atoms, but ultimately all the individual corpuscles of strings that combined in all the diverse and sundry ways that cause that apparent physical object to come into being. So this is straight up. This is physics. This is real physics. What I'm saying is not, in the way I'm describing it. So that's accepted. People believe this is what happens. Um, so I guess if I want to describe the essence of energy, once we get it to a macroscopic level, like the way that we walk around and we see. Oh, I guess the point that I was going to make before I went to that point is going back to the movie. Um, since everything is really just energy vibrating, it's not unreasonable that I could make some sort of analogy with what I was doing with sound, is that if you could have something that is vibrating with such a high frequency, its collective vibration so high that it's out of the range of not only what is your body or what you see or all the range of frequencies associated with your physicality, it could be such that it is out of the range of the physicality of anything that we see in our natural world. Now, what we call natural is the things that we see, but frequency is just frequency. It's just like a rainbow. Like this, this reality that we see here, it everything is just vibrating physically within a certain range of frequencies that for us, we assume the conventional, well, it's not anymore, but conventionality says that nothing exists other than what you can interact with. But if you think about it, it's a completely ridiculous statement. Now that we understand how that matter works just like anything else, there could be whole ranges of frequencies, even in the universe, that are so far out of the range of not only what we can physically interact with because of our natural senses, but even things that we can create. Because we can detect microwaves and gamma ray things that are out of the range of our frequency naturally, but not out of the range of the frequencies of devices that we can make. And there's only seven electromagnetic waves. So our range of matter waves is, light waves and matter. Well, lights are seven different light types of light. But you could also describe matter in that way as well. We don't usually when we teach it, but you can. And so what I'm trying to say is that just like there's a range of light, you can think of matter as just light that's slowed down, that's very slow. Energy that's slowed down with this vibration is very slow, but it would also have a range, which implies that there are an infinite number of ranges that are so far out of what we call our world that there could be stuff there and we just don't even, not only we not see it, but we couldn't even feel it or interact with it. It basically isn't there. It could walk right through you and be real, just as real as you are, but you would never know. Just like the dog whistle, the frequency of the dog whistle is right there. It's vibrating, it's all around you, but you can't hear it. Only the dog can hear it. Now, what I just told you is absolutely straight up solid physics, right? So it's not like conjecture or, you know, whatever. Um, so yeah, and I'll leave that at that, with the exception of one more thing I want to say, implication I want to just put in your mind to have you think about before we get back to the last thing I want to say about the energy before I go back and work the stuff from the last chapter. When you look at a rainbow or any dramatization of a rainbow, or even if you were to take white light and run it through a prism and break it into a rainbow, uh, what you see is that what I've just told you about the extremes outside of that, like that's just a small range of other ranges of electromagnetic radiation that you can't see, and some of which we can detect, some of which, not all of which, because I'm thinking it's infinite, but some of which, and those things that we can't see but we can detect are all the other six electromagnetic type of rays that we name that are parts of the overall spectrum that white light is just part of. But again, even the 7 is just a small range in an infinite number of ranges of electromagnetic waves that could theoretically exist. When you look at the white light and you break it into its spectrum, you can see when you look at the cusps, meaning the boundaries, that those boundaries are not crisp. They are when you're very far back, but when you start to get close, meaning you have something that can kind of have smaller and smaller wavelengths, what you see is that the boundaries mesh into one another. Those boundaries themselves can be split into infinite spectrums. We don't do that. We just cut it off. White light is or gamma rays is this range. Well, we do say a range of frequencies, but even when we get to the range, like gamma ray is from some low frequency to some high frequency, but then the next range is that particular high frequency to the next high frequency if you're going on the top. But what I'm saying is that when you look at that boundary, that high frequency, it's not crisp. You could take that boundary and basically split it into an infinite number of frequencies itself on another order of magnitude. So it's not just infinite that going on in terms of the ranges, in terms of like say a factor of 10, going up and down the spectrum. Even within the boundary, you can start to go into tenths and thousands and hundreds and breaking down into an infinite number of spectrums that way as well. Now that is light. So two things that I'm taking from that point, that the boundary is not crisp and it has an infinite number of ways to break it down as well. Now, when you take that to matter, and are you making the analogy with matter that all the frequencies of the vibration of anything on the earth that is we consider solid that's matter, that think of that like a range of frequency like the white light that I just said. Now when you go to the edges of that, there are things that could be matter that are so low, such a low vibration that we don't see them, and things that are such a high vibration that we can never see them. But on those boundaries are the cusps, and within those boundaries one boundary can bleed into one another. So when we kind of look at these, it's October, it's Halloween, you got all the scary movies coming out, and the concept of ghosts and things like that, or even not ghosts, just other types of. I guess what I'm trying to imply is that if there are sentient type of beings or life that can actually exist and just happen to exist at a frequency or vibration that is beyond what we can physically sense, then maybe that is a starting place for an explanation for that type of phenomena. That even things, like angels and things that can come and go. I don't know. Like, I don't know. I'm just saying that once you understand matter from that perspective, then it makes things like that not ridiculous. There's and not some unexplainable. I mean, I, not something that seemed like, in other words, I don't believe in magic, and I don't believe in. I mean, these terms are just terms that we have for physical phenomena that we don't understand. But once you begin to kind of open up to different points of view, particularly about the implications of what quantum mechanics is saying, and then take that and then reconsider things that were seemingly unexplainable, it actually starts to make a little bit of sense as to how these things might be. So if matter can be described in ranges of vibrational frequency, and it can, according to quantum mechanics, there's no question about that, from the macroscopic down to the smallest level, then, and we are sentient, and so we are sentient vibrating corpuscles of energy, then you could have sentient vibrating corpuscles of energy in ranges of frequency that are beyond what we can see. And if you're at the cusp, maybe that's a place where things can bleed in and bleed out. So when you look at something like in the movie, it's becoming popular culture. And some people speculate that a lot of these things are being put in movies now so that it can begin to acclimate the public to what used to be considered fantastical ideas that are not fantastical, anymore, considering what we think we know. What that dude is doing in that movie when he starts to vibrate himself and then walks through a wall is absolutely theoretically possible. The idea that a sentient being, if they could control their vibration, make it higher or lower, control it in such a way that it low, if they're higher than us, lower it so that they come into a place where we can see us, that we can see them, and then disappear. That's how you would disappear. And how you would, like in the movie, the guy is doing it mechanically because he can physically shake himself. But another idea, and then I'll say this and let it go, and we do it all the time, mind over matter. Thought is more powerful than, you know, than the material world that we see. So if you want to manifest, I mean, we talk about that all the time. But what I'm trying to say is that there's a physical basis for that. That thoughts are also energy. Everything is energy. And when you have a thought, it has a certain, we say it in lay terms, but it's actually true that when you have a thought and you just look at the the impulses in your uh, nervous system, electrons moving around, that sort of thing. Well, what is an electromagnetic wave? An electromagnetic wave is just a vibrating charge. So our thoughts are literally, uh, physiologically, there are literally charges changing. I mean, I'm not a biologist or physiologist, so I don't really know how to speak about it in the more precise terms. But thoughts, you have neurons popping off and things like that. So they're sending out waves, brain waves. Those things that you measure, they're showing in those are actually waves that are leaving your head and going out because they're waves that always do that, right? So those things can affect, it's not unreasonable that a thought can actually have power to change things. And it's not unreasonable that if you had control of that and you can make it strong enough, it might be able to change things, like you might be able to change your physical vibration by thinking and focusing on certain thoughts, to do that with thought, as opposed to having to only be able to do that with a mechanical vibration, which is what the guy is doing in the movie. And so, but still, the end result is the same. If you can raise or lower your vibration, then it changes your physicality. And you can do things like walk through walls. So, you know, that's what energy is. It's ultimately the only thing that actually exists in the universe. And these strings are on a level that's so small, it's just hard, it's unimaginable. But we call it the Planck scale, and it's between 10, it's I think the Planck length, which is the smallest length that anything can be measured or exist, is 10 to the negative 34. Planck's constant is on the order of 10 to the negative 30. Well, actually, I think the length is 10 to the negative 35. Planck's constant is 10 to the negative 34, which is the smallest amount of energy that can exist. So these corpuscles of vibration, that's the constant that basically energy is equal to something called Planck's constant times the frequency of vibration. And so all these kind of the lowest particles that exist are basically corpuscles of vibrating strings of energy that are just fill the universe. They're everywhere. They're everywhere around us, even right now. I think I made the analogy before. I've been talking about this in my E&M class, so I'm not sure if I said this before. But a nice analogy is water. You know how everything comes from water. We have the ocean and the water molecules. You can't see them, but you can see the collective result of them. And everything in the ocean, from the plankton, the smallest microscopic particles, to the whales, came from the water. In the same way, make the universe a globe of strings, just like you can have a a sea of water. So the strings, the vibrating corpuscles of energy are analogous to water molecules, and they're not all, and they actually are the fabric of space time, really. And so they fill everything all around us. But if you could, if the smallest particle, that smallest length that you can kind of visually imagine, at least me, I can imagine a millimeter, right? That's, if you can take a ruler and look at it, it's right here. It's like the smallest increment of measure on this thing. So a millimeter is 10 to the negative 3. But these corpuscles of energy are 10 to the negative 35. So you could see that, in fact, they're even smaller when you compare the size of a whale, for example, to a water molecule. The size of a person to a string is probably 10 to the 20 times even you know smaller in magnitude than that. Or I have to work it out, but very much smaller. Maybe even more than that. Maybe more like whatever. That probably isn't. It's probably more like 10 to the 29 or 20 to 28 or something. Anyway, the point is that still you can kind of make an analogy like that, that everything came from strings, just like, life, physical life came, that we, on the earth came from water, or ultimately, was on the level of water. And then you had cells, um, I don't know. I don't know. I can't speak the biologically in a way that gets the progression. But you get what I'm trying to say. And so the universe is just filled with these corpuscles of strings, and throw in something else. Apparently, it's conscious. The energy. Uh, but again, that's a different kind of discussion about that. And so these corpuscles of energy begin to come together and form ultimately what turns into what seems like tangible matter that seems separate from everything else in the universe, just like the mammals and the reptiles and the fish in the sea somehow seem separate from the water molecules. But that kind of illogical because they came from them. So same thing with the strings and the universe. Everything in the universe is really just the strings, but vibrating at a very different level, so much so that they seem separate. So there's only one thing, and it's just the universe and the energy in it. Again, that's straight up physics. But when you say it like that, it starts to sound very similar to a lot of language that we hear, have been hearing, most of us in all our lives, in philosophy and religion. Right? So don't want to go there, but just pointing out that this is what is, come out of this is where the discussions are on the cutting edge of trying to the theory of everything and trying to understand, grand unification of the four. And if we find this grand unification, this what Einstein called it, this fundamental force, that force quantitatively, qualitatively will be able to explain everything I just talked about from whatever perspective you want. It's the theory of everything. That's why they call it that now. The theory of everything, everything meaning everything. So that's what I would say energy is. That's my best explanation. Energy is literally the only thing that exists in the universe. So to say where it comes from is illogical and makes no sense. It is the only thing that there is. Everything else in what is it? Well, it is itself. Energy is energy. That's all I can say. What we will do in this class is look at it from a macroscopic point of view. We won't go down to the quantum level. We'll do the way to physics 39 to do that. But I do want to qualitatively describe it to you so that you understand and you can kind of see the big picture. Now, what we're going to do is focus in on a macroscopic level, and even on a macroscopic level, even though the simplest level, which is just mechanics, which describing two types of energy. Well, one type, but I had two forms. Because there's, even on a macroscopic level, there's different types of energy. Heat energy is different than mechanical, is different than electrostatic, which is different than magnetostatic, which is different than electromagnetic. Those are all different ways that the energy manifests itself based on the things that we interact with: matter, light, matter interacting with other matter through, moving and position. Um, it's just these are just all names for the same thing that has manifested itself differently as it has created what seems to be our physical universe that we can acknowledge and see and interact with. Um, so that's a really long topic or a really long discussion. Maybe not that eloquent because not that eloquent today, but I think it does the trick to give you a kind of comprehensive view of what we're talking about when we're talking about energy, and at least qualitatively. And so now we're going to go in and try to quantify it by looking at very specific types of examples in the way that that energy manifests itself in very large, slow particles like us and balls rolling down planes, and look at what happens with that energy during those interactions. So before I leave that and go back and talk about centripetal force, any comments or questions about anything that I said here? Okay. So, and just because of the nature of some of the things I said in this discussion and something that was brought to my attention a few weeks ago, I think we got into some discussion maybe 2 or 3 weeks ago, and it kind of someone mentioned something, or maybe I did, and it sparked some conversation that about where some ideas about theology and philosophy came into the class, and I was, because I can't see you, and because I can't, I'm not, didn't really pick up on. It's hard to kind of interpret how you're taking things because I'm talking to basically, a blank screen or screen with no faces. But I think some people, it was, in, it seemed that maybe one or two people were offended by the conversation that we had, and because it went in that direction. And I think so. I just want to say that physics, first of all, these things are appropriate, in my opinion, for this class. Because when I started this class, I told you that physics is the study of the physical universe. Now, a lot of people think that you have a limited point of view of that if they haven't been in a physics class or not a physicist or don't know anything about science. But basically, when you make a statement like that, the physical universe is literally everything you can think of or conceive. You can see everything you can see or anything you could think of seeing, anything that you could possibly. That's the physical universe. So everything means that when they, like, again, going back to the theory, it's no accident that it's the physicists that are trying to come up with this theory of everything, not the biologist or the chemist or any other scientist. It's the physicist, because the physical universe is literally everything, thought, you know, anything that you could possibly think about. So ultimately, everything is fair game to talk about in this course, because everything that we have come up with as a species is just ways of trying to different perspectives of trying to figure out the physical universe. So that's why it was appropriate, and it may not be obvious if you don't know that coming into it. And that's why sometimes I kind of lean to that, just to put ideas in your head about the implications of certain things. Um, so that's my justification. And but like, we're not there yet, and we're not like this. It's not we're still building up the rudimentary building blocks of understanding how to approach studying the physical universe. So that's fair. I'm not going to spend a lot of time doing that, but I do want to. I try to keep the bird's eye view, or as big a perspective of a subject or a topic, you know, have that um, have you be aware of that, because it places context for ultimate context of what we're talking about. So yeah. I just wanted to mention that because I'd been thinking about how to say something about that for the past week and a half or so, and so it just felt like maybe this was a good time to say that. So before we get back to centripetal force, any comments, questions, troubles, gripes, complaints? I will hear it without, it's a free and fair and safe environment. So you can say anything, you want and respond, and you're free and to have your opinion about whatever. So anything before I start.
So just a side question, Professor.
Yeah.
So it's not really about the topic, but I was curious. How many forces can be present in on an object
That's a great
overall?
question. Well, I would answer that this way. There's only four forces. There's gravity. There is electromagnetic, which used to be two, and there's the strong and weak force, strong nuclear forces and the weak forces. And honestly, Arcady, the I think accepted answer from most physicists, many, all basically, who I think, basically, is that anytime you encounter any force at all, you're always encountering all four forces simultaneously. Always.
Really?
Yeah.
Okay.
But but when we talk about at this level, when we break them down and we say that, well, you're only dealing with a gravitational force, or you're only dealing with a frictional force, it's a simplification. It's a simplification because the contribution of other specific forces might be so small relative and under those circumstances relative to the overall force that we just negate them. We would just say, well, it's just this force acting this way. Yeah. But that's why the forces are fundamental. Because if you think about it, like right now, I'm pressing my hands together. I call it a normal force, right? That's what we say. Newton's third law. But what's keeping my hands from meshing into one another? It's the fact that the strong and weak nuclear forces are so strong that they're preventing one hand to go into the other. So the normal force is, and also there's still gravity there, right? Because there's a gravitational attraction for my hands, and there's charges. Like there's, if you go, because I think or have I? Well, I might not have shown you because we haven't had. Yeah, I don't remember. But usually, I early on, I'll describe something called the Einstein model of a solid, which shows how atoms, a basic model of how atoms broke down and how they're kind of collected for different objects, how they're organized. So on the edge of my hand, you have the atoms of my hand, and those atoms, they're bound together by bonds and they have electrons. So if you could see the boundary of my hand, it's just like a lattice of atoms that are together. And have charges around them and stuff, and are vibrating with their own natural vibration. So what's keeping my hand from going into the other? The fact that the bonds between the atoms of one hand are so strong that they prevent the atoms of the other hand from getting into them. So if you break the normal force down on a microscopic level, it's just going to be a combination of all the forces. But we kind of collectively talk about like the macroscopic result of the pressing together, thinking about the hand as one flat surface, and we just call it a normal force. So
That
that's one
is very
example of
interesting.
breaking it down. But you could do that with any force, we can, like, yeah, I'm sorry, go ahead. I cut you off. Go ahead. Go ahead. Yeah.
Oh no, I just want to say like, that was interesting.
Yeah. Yeah. So, and that kind of it's that question in my answer, it is a kind of a nice explanation of something that I had said early on in that conversation about energy, where, I talked about looking at energy on the Planck scale as opposed to larger scales of the macroscopic scale. Like you can't really see that I'm energy and just vibrating corpuscles of energy because, those corpuscles are on the order of 10 to the negative 34. and my hand is like on the order of 10 to the 1. You know, you know? Uh, so we're just in mechanics, we're just kind of naming these things macroscopic terms that are just, average descriptions of how, almost an infinite number of particles are behaving in different ways on the Planck scale. Yeah.
Okay,
Yeah.
got it.
Okay. All right. Anything else?
Thank you.
Cool. All right. I guess I better get up and do some work now. So let's switch gears. We'll come back to that near the end of class. Centripetal force. This thing is hanging right now. Now, we describe centripetal motion as, well, we had a special case of centripetal motion, which was uniform circular motion. We said if something is moving around, I think that how I started the question for you back then was, if this thing is moving around at a constant speed, does it have an acceleration? And so it's kind of a trick question, right? Because acceleration is a change in velocity, not a change in speed. The speed is the magnitude of the velocity, but because velocity is a vector, having both magnitude and direction, there's two ways that it can accelerate. The way that we normally think of is changing its speed. But even if its speed doesn't change, if its direction changes, then it also has to have some kind of acceleration. So that's the case here, that even though the speed is constant, since the direction is continuously changing, the type of acceleration that we have is called a centripetal acceleration. And I didn't derive that for you. I just wrote it down. And so I'm not going to derive it here. We're just going to move on. But yeah, so, and we talked about that. And so we said that, I'll write it down in a second, but we defined the centripetal acceleration as the square of the speed, v squared, over the radius of the circular motion in which it's occurring. And we said that it always it's always perpendicular to the direction of the velocity. So if you're moving in a circle, since the velocity is always tangent to the circular path, the direction of this acceleration is always pointing toward the center of the circle, which is something is also a little weird, because with linear acceleration, the linear acceleration is either parallel or anti-parallel to the velocity. Parallel if the object is speeding up, anti-parallel if it's slowing down, if it's decelerating. So those are a couple weird things that we had to understand about centripetal acceleration, is that it's not, it's equal to this, the square of the speed over radius, and it points in a direction that is, 90 degrees to the direction of motion, which is very, is counterintuitive. Now that we have Newton's second law, we know that whatever kind of acceleration there must be a force associated with that, right? Because net force equals mass times acceleration. Now, the kinds of acceleration that we've thus been using Newton's law to describe has been linear acceleration, where the net force is either parallel or anti-parallel to the direction of the motion. But since we have this thing called centripetal acceleration, there also has to be a centripetal force that is associated with that acceleration. Okay. So yeah, it's just that. And if we then apply Newton's law, second law to that, then we say that the net force, if an object has a centripetal acceleration, then the net force on that object, and really would be along the direction of the acceleration, but the net force along the coordinate direction that describes the centripetal acceleration is got to be equal to the mass of the object times that centripetal acceleration. Now, what I want to say about that before I go to the board is that we're going to work with several problems, maybe starting with that one, the one that I was just doing, where we describe an object moving in a circle, and it will have several forces on it, some of which will be along the direction of the centripetal acceleration, some of which will not. But it's important to understand that, because this is the first time I think you're encountering this, that the centripetal force is a net force. It is a net force. Net meaning a superposition of forces. And it will be a superposition of forces of all of the other types of forces that we have talked about up to this point, and some that we will talk about subsequently. And I don't really have a name for this, but I guess I would say natural forces. So the centripetal force is always going to be a sum of all the natural forces that we can have discussed and will discuss in physics. Natural forces, meaning the fundamental forces and contact forces and whatever other kind of practical, tangible, pragmatic force that you could describe. So the centripetal force will be a sum of all possible forces like gravity, magnetic, electrostatic, tension force, normal force. Well, not, but because of the nature of normal force, but frictional force, anything, any kind of these are the natural forces I'm talking about. So when you start to work a problem, you identify that centripetal force is involved simply because, as I've always taught you, you have to evaluate the motion first. If there is centripetal motion going on, then you know there's a centripetal acceleration, which means that the net force has to be a centripetal force. That's the only way that you know, right? In the same way I told you that when you evaluate the forces on a problem, which law applies, the first or the second? Well, is there an acceleration? If it is, then it's the second law. If there's no acceleration, it's the first law. We can now extend that to what type of acceleration is it? Is it a linear acceleration or is it a centripetal acceleration? If it's a centripetal acceleration, then the net force will be centripetal. So then you go ahead and identify all the natural forces on the object and then approach the problem accordingly. What I'm trying to tell you is that there will never, ever be a time where you have to sum all the natural forces, then put in something that is a centripetal force in addition to those. That is a fundamental error. It doesn't exist. What I'm saying is that all the natural forces that you have been studying, those will be the only forces on that object. It's just that they will sum to be equal to the centripetal force. That's equal to the mass times the centripetal acceleration. So there's no need to write all the forces on the object and then say, oh, well, since it's going in centripetal force, I got to draw in a force that's also the centripetal force in addition to all those other forces. That was going to cause you to be, that's a fundamental error and fundamental of understanding of what centripetal force is. So it's never that. So like when we look up, so we know, like, for example, well, I would say, like, so we got the Earth, we got the moon going around us. Now, it's an elliptic orbit, I know, but like if we just assume a circular orbit and we assume that the moon has a constant speed, then that's uniform circular motion. And we can say that, the moon is going around a circular path, and so it's experiencing centripetal acceleration. So what are the forces on the moon? What are the forces? Well, clearly there's a gravitational force on the moon, and it's pointed straight toward the center of the Earth. It would be incorrect for you to say, well, there's a gravitational force, but because we know that it has centripetal acceleration, there must also be a centripetal force. So there's two forces on the moon. There's gravity and the centripetal force. That is wrong. The only natural force on the moon is gravity. So when you analyze it, the second law, net force equals mass times acceleration. What type of acceleration is the moon experiencing? A centripetal acceleration. So the net force on the moon must be equal to a centripetal acceleration. Now that you understand that, go in and identify all the natural forces on the moon and add them up. It just happens to be one, gravity. So gravity then is the only force on the moon, and it equals the mass of the moon times the centripetal acceleration of the moon, not gravity plus some other force that you call F centripetal. In that case, gravity is the F centripetal. If there were other forces on the moon, other than gravity, that contributing to that, then you would add all those forces up, and all those forces would be equal to the centripetal force. That's what a centripetal force is. It's always a net force of natural forces, given that the motion of the object is centripetal. That's how you have to approach it. And the final thing I want to say about that is before Newton's time, again, going back to Newton and his genius, when people looked up, they said something like, oh, there's the moon. It's in the sky. It's not falling. So we know there's gravity because things fall, but there must be something, because when I hold a rock up, I drop it, it falls. When I look at the moon, I know there must be gravity on the moon because it's not floating away. So the Earth's gravity is keeping it there. But there must be another force equal and opposite gravity that's keeping it from falling on us. So, okay, we'll call the force that's toward us centripetal, the thing I've been talking about. But the force that's opposite the moon, we'll call that centrifugal, as in centrifuge, centrifugal force. So the centrifugal force, so there are two forces on the moon. There's a centrifugal force that's pointing back away from the Earth, and there's a centripetal force, a centripetal force that's toward us, and they're equal and opposite. Well, no, that's wrong for a lot of reasons, but it would seem obvious. It seems intuitive, right, that makes sense. Well, when Isaac Newton came along, what he said is, well, you know what? The moon actually is falling. It's falling. So one, that alone says there's no reason for a centripetal force because it is falling toward the Earth. It just never hits the Earth. And this is how he explained it. He said, okay, let's say that we can build a big cannon and we can put it on the North Pole. And this drawing and sketch that I'm about to make for you, he actually published it in the Principia when he published the laws of motion, this thought experiment. Incidentally, that idea about stuff going through things because they're so different vibration, that's what certain types of gamma rays do, right? They go through the Earth, and we can only detect them because we make devices that can absorb them. But the interesting point is that if you're on a gamma ray and you're going toward the Earth, right? And for what we say is that it goes through the Earth. But if you're on a gamma ray When you come toward the Earth, what do you see? If you could see, if the gamma ray could see something, what would it see? And the answer is that it wouldn't say that it's going through the Earth because it wouldn't even see the Earth. It can't. It's like there's nothing on the Earth that's even remotely close to the vibration of a gamma ray. So for all practical purposes, the Earth isn't here. So the gamma ray doesn't think it's going through anything. There's nothing there. So that's kind of a mixture of light and matter, but in the end, matter is light because it's all energy. So that's a good example of how, the explanation of what I was trying to say, right? That, uh, yeah, that, there's nothing for the gamma ray to go through. So that's kind of what happens when you can, like, was there. And they tried to show that it was kind of clever. It's hard to show that, right? But when the guy is vibrant, that's why he would disappear if he was going, that vibrating that fast. Like he would disappear and just walk through the wall. There's nothing to go through, right? I don't know how they tried to dramatize that by looking at Adam's back. I thought it was pretty clever to do that, but that's what it's trying to illustrate. So Newton and the centrifugal force. So here we go. So this was Sir Isaac's argument. Here's the Earth. I'm going to place a cannon. It's not very circular. Place a big cannon here on the, and actually, let's make it shoot horizontal, straight out, like that. This is Mother Earth. So, if you throw a rock or shoot a projectile with a speed that's much lower than the escape velocity of the Earth, we know that it experiences parabolic motion. We've talked about that. So what happens is it comes out horizontally, then it falls to the Earth in a parabola. If you shoot it faster, it just comes out and falls farther down range. If you keep shooting it with higher and higher speeds, it just falls farther until you reach a speed that is so high it reaches escape velocity. Actually, this is not really escape velocity. So cut that. Orbital velocity. So because it escapes when it escapes the orbit. So it's not escape velocity, it's an orbital velocity, which prevents it from falling back to the Earth, but it still falls. It just continues to fall around the Earth without hitting the Earth. So that's what satellite motion is. It's falling toward the Earth without hitting it. So when we see the moon, just because it's not coming toward us doesn't mean it's not falling. It is. And any satellite, it's always falling. It's in a continuous state of falling, and it's at a certain energy state, kinetic energy state, such that it can fall at different higher and higher radii, depending on how much energy. The more energy it has, the higher the radii at which it can fall around the Earth. And there's another limit. There's a critical limit between the range of satellite velocities that can exist for a particular mass relative to our Earth, such that if you go beyond that energy, you then escape the satellite, orbital satellite. You escape orbital motion. So it's kind of three regimes. One regime are speeds between 0 and the lower than that, you're going to fall and hit the Earth. So between some critical satellite speed and a critical escape speed, all those ranges of velocities you'll orbit around the Earth, but at different radii. Once you go beyond the critical escape velocity, then you orbit, but you escape your orbit and you can leave the Earth. So just ranges of energies that describe that. Yeah, so if that's the case, here's the moon out here. It alleviates the argument of saying that you have to have, here's the moon, and we know that there's a gravitational force that is, well, pointing. We haven't talked about it with so much yet, but like we talked about only in the context of the second law. But yeah, there's a gravitational force. I'll just call it mg. I won't even call it, or f of g. I won't even describe it in terms of the universal law, since you don't know that yet. But yeah, and it's always pointing toward the center of the Earth. And since I know that this moon is experiencing uniform circular motion, then whatever its speed is, that speed must be equal to, have an acceleration that is equal to v squared over r. So centripetal acceleration we define as v squared over r. Now, in the case of the moon, r is the distance that the moon is from the center of the Earth. So when you do a practical problem like that, you can't just think of the distance from the surface to surface. Basically, that distance is always going to be the radius of the Earth, the radius of the moon, plus the average value of the distance between the surfaces. But given the speed of the moon, which you could figure out just from looking at a calendar, you could, and knowing the radius of curvature of the circumference of the moon, you could figure out its speed, and you have its centripetal acceleration. Now, centripetal acceleration is always pointing toward the center of the circle. So that centripetal acceleration that you would calculate as the moon goes around is always pointing toward the center of the Earth. Now, so because of what Newton said, there is no need to have so centripetal force. So what I was trying to say, I said it, I think, pretty clearly, but let me say it here now that we're quantifying. This thing is accelerating. That's the first point to make. It's accelerating, so Newton's second law applies. Net force equals mass times acceleration. So it's the second law. Now we have to go one step further. This is not a linear acceleration, but by evaluating the motion, we see that it's centripetal. So if I put a C here to represent centripetal acceleration, then I have to put a C around the whole thing here. That's what I'm saying. This whole thing is a centripetal acceleration. That is it. That is the centripetal acceleration, that net F. Now, when I apply that and analyze the left side, just like I've been teaching you, you do not go in and at some point put anything other than just the natural forces that are on the object. So in this case, the only natural force that's on the object is Fg, right? So that's what this net force is. And that equals the mass times the centripetal acceleration. So in this particular case, gravity is acting like a centripetal force. It's not an inherent centripetal force. It doesn't always make things, move around at a constant speed. It's just because of the nature of the physical situation there. It's doing that because it's the only force on it. It got shot up somehow. We don't know how the moon got there, but satellites, you get there, it has some speed that it's faster than the speed that causes the object to fall down to the Earth, but not fast enough to escape the orbit. So it's a satellite speed. It's in that range, and so it's moving around like that. But gravity was always the force that was on it, and it's still the force that's on it now. So since it's accelerating, like if you had a force here equal and opposite, it would imply that those forces are zero, but it would imply, so if there is actually a centrifugal force, I'll spell it out, fugal force, it would imply that the acceleration is zero. So the acceleration is zero because it's the first law and there is no acceleration. That's not true. It is accelerating based on everything we've defined because it's moving in a circle and the velocity. In other words, that would violate the fundamental definitions of the thing. If there's no acceleration, and if acceleration is changing velocity per unit of time, and the velocity is clearly changing because its direction is changing, then what gives? Like, it makes no sense. So the thing that doesn't make sense is this. That's not true. Now, there are people, and I have to admit, even when I graduated undergrad, I couldn't explain this. I thought, well, I couldn't explain it. Yeah. And even now, you will talk to people, educated people, who will look you in your face and tell you that there is such thing as a centrifugal force. In fact, for some reason, even after maybe they didn't believe him. I don't know, because he was a young guy when he did all this. He was like 22. And there were people who were trying to refute him, like for years. So I don't know why this is one thing that kind of slipped through the cracks, but for some reason, the word centrifugal never people kept using it. We can still, and even to this day, we use it. We say, when you go to like in chemistry, the thing that separates the thing that separates the particles and stuff, it's called a centrifuge. We have kind of a mechanical one that we use separating, like when we go to the when you go swimming at a really nice swimming pool, and you dry your swim trunks out. That thing is called a centrifuge for the same reason. When you go to the fair and you get into the thing, there's a centrifuge that you start spinning around, and you stick to the wall. And everybody says it, but when they use it, they're using it for the same reason. They're trying to say there's some force that's pushing you out. There is no centrifuge. There's no centrifugal force. That's not what's happening in all of those cases. And we can do the example, especially the centrifuge, the circus thing. There's only a force that's pointing toward in the case of the centrifuge, it's the normal force. You stick to the wall, the normal force is pointing toward the center, right? It's the force of the wall on you. And that's the only force on you. There's no other force. There's no force pushing you out. And it's really counterintuitive, but that's true. So in any case that you can ever think of, any place that they use the word centrifuge, there is no centrifugal force. But for some reason, we kept using the word, so now it's in popular culture, and that's what everybody calls it. Right? Calls that phenomena, or when that's set up. So there's a couple of things I want you to understand when you leave this class. If someone comes up and asks you what's Newton's law, you better say F equals ma before you can even blink. And a couple other things. But if someone asks you, if you see it on a standardized test somewhere, if there is such thing as a centrifugal force, you need to say no. There is no centrifugal force. It's a pet peeve of mine. Clearly, I have emotional response to this. It's kind of funny, but it's really interesting. It's interesting how something that was wrong and maybe people thought was a valid, because it does seem to make sense until Newton comes along and explains it. So I don't know the history, but I'm guessing that it probably existed within higher echelons of education, that idea, for a long time before Newton came along and disputed it and proved that, with his laws of motion, that it's not true. But, people just kept using it because maybe they didn't have valid proofs. Same thing happened with light. That, when Maxwell came along and said that, well, he didn't say that there's no ether, but he said that light doesn't need a medium like what we thought. And so it's just an electromagnetic wave, and it can go through space, whatever. And he did this around 1860, but it wasn't until almost 40 years later, 1895, that it was indisputable. Before that, most scientists called him a liar and said that no, ether exists. I don't know what's up with you, but it's not true. And this thing you call speed of light that has some fundamental speed, it's like the maximum. I don't know what you're talking about. So until we could create devices to measure the speed of light and prove it, people still believe it. But for some reason, once that happened, everybody embraced it and then left the archaic stuff that they, did not believe, left it alone. Now we kind of come back to that full circle, because this whole thing I described to you about strings, some people are now saying that is actually the ether. And they might actually have a point there, that actually there's ether after all. And because we now know space is not a vacuum. It's full of strings. And light that's coming through that is not going through a vacuum. It's going through that stuff. So maybe there might be a perspective going through the strings. Maybe there might be a perspective that might describe, I don't know, some relationship between that and light. And I don't know if we've done that. I don't know how to do that. But just as a caveat for that. But going back to this, once Newton proved it, for some reason, people kept using the term. It stuck and it never left popular culture, even to this day. But there is no such thing, people, as a centrifugal force. It does not exist anywhere, under any circumstances, under any device that you can have. This basic example that I showed you is the explanation of all those scenarios. Now, there are some scenarios where you have more than one force on an object that's contributing to that centripetal force, but all of those forces will always be pointing toward, and you could even have forces in the opposite. It's possible. It's not going to be a centrifugal force. It might be some other kind of force. I don't know. We have to come up with some example. But the net force, the sum of all those forces along the line that is parallel to the centripetal acceleration, the net force will always be toward the center of the circle. And all those other forces, any force that might be opposite direction, they will also be the natural forces that I was talking about. They're not going to be the natural forces plus some centrifugal force, right? So no. There are not individual forces that are either centrifugal or centripetal. In fact, there is no centrifugal at all, period. The centripetal will always be a summation of all of the other natural forces. So the centripetal does exist, but it doesn't exist as a separate independent force of itself. It is only a summation of all the natural forces, period, end of discussion. Is the moon always moving because of Earth's gravity, or is it because the moon is in a vacuum? Let me think about that. Yeah, I would say both. I would say both, because if it were not in a vacuum, there would be some drag force or something slowing it down. And I don't believe there's any other kind of force doing that. So that's the answer to that. And it continues to move because it's the first law, basically, kind of a variation of the first point that you were making. It's the first law. The first law says that unless there's a net external force that comes along, it's going to continue to move. Now, there is a net external force on the object, but it's not a force that's causing it to change its, like if I came along and I had a force that's parallel to velocity, it would make the thing speed up. Like, for example, a rocket. Like, say it's a rocket moving around, right? And the rocket's off. But then I shoot the rocket such that I give it a force that's parallel to the velocity. And remember, I don't know how to. I think the moon actually orbits kind of. Well, it depends on how you're looking at it. But if you're looking down from the top, well, let's see. Yeah, counterclockwise. Or clockwise, I'm sorry. So the moon actually orbits like that, right? Because, wait, what? It comes in the east and sets in the west. So if I'm in the North Pole, actually, I guess the North Pole would have to be pointing out toward us. Yeah, so if the North Pole is out pointing toward us, then the east is clockwise. So yeah, the moon would be orbiting like that if the North Pole is out. So I messed up because I said I put the North Pole up here. So if that's the case, then this is wrong. So forget that just say this is on the Earth someplace. Don't think this is at the North Pole, because if this is the North Pole, the moon has got to be doing something like that. So so this is not the North Pole. It's just some arbitrary position on the Earth. I didn't think that through, actually. But yeah, if if the moon is, is orbiting like that, and I take some rocket, engines or something, and I put on it so that the thrusters thrust it in that direction, then, and we kind of, it's a rocket, it's thrust. So even though it's technically, I guess, not external, um, it's behaving like an external force, and we have a whole way of dealing with that, which I don't want to get into right now. But that would change the velocity of the Earth, of the moon, and it could change it so much so that it could cause it to escape, achieve escape speed, such that it would just kind of get fast enough and just spin off. So that's not happening. So that implies that there is no force on the external force that's causing the velocity to change. So there's no linear acceleration. The centripetal acceleration is such that it's causing the direction to change, but not the magnitude of the speed. So it stays there. Now, actually, I don't know if you heard, but the moon actually is moving away from the Earth. I think it moves a certain amount of millimeters I don't know what it is, every year or something. And ultimately, it's going to escape. Now, I'm actually not sure that we know why that is. That's a true statement. The moon is moving away from the Earth, but I don't know if we know why. Because based on what we think we know about the moon, because it shouldn't, as far as I know. Yeah, but there's some other things that to consider that are natural. Like, for example, the orbit of the moon is not circular; it's actually elliptical. But even with an elliptical orbit, if the energy is constant, it stays in its orbit. If it loses energy, its orbit decreases, even for ellipse. If it gains energy, its orbit increases. So if this thing is moving away from the Earth, a few millimeters every year or so, yeah, and I haven't studied this, but my first impulse is like, where's the energy coming from? It's got to be some external energy source, which implies an external force. So, and implies that the velocity is not staying the same. So I don't know. I don't know. I haven't researched it, and I don't know any explanation. If there is one, they haven't put it out. There's a whole lot of conspiracy theories, but I don't know if those are. Yeah, I don't know. But it is a true statement that the moon is actually moving away from the Earth, and it won't escape for thousands of years or something like that. I think, but it is moving away. So does that answer your question, Mikey? Is that a satisfactory answer? Yeah.
Yeah.
All right. So yeah, what I want you to get from that is that there is no centrifugal force, and people get angry about it too. They dispute you. Yes, there is. Okay, but no, there is no centrifugal force. No such thing. But you can still use the word if you want. That's what we do. Let's get to this problem here. Let's analyze this problem. So this thing is moving around. Let's assume that it's a mass and it's orbiting at a certain radius with a certain constant speed. Let's see if we can apply. I'm going to give you the mass, the angle of motion relative to the vertical, and the length of the pendulum. And from that, we are going to apply Newton's laws and analyze the motion. We're going to get the period of motion, the frequency, and everything. Well, actually, we won't do that too. No. So I just want you to get that. We need to do get the oscillatory motion to do that. So no, we won't do that. What I want to do though is find the speed of the so given the angle, the length, and the mass, what is the speed of motion? How fast is it moving? And also, what's the radius of orbit? So let's do that. And we can now do it now that we have this equation here, now that we have Newton's laws for centripetal force. And everything else we talked about previously applies. The frequency, period, all that stuff that we define, all that stuff, writing the centripetal acceleration in terms of the frequency and period, we did that already. All that stuff still applies to this. Now, what I'm going to do is I've got to evaluate the forces on this. So I'm going to take a snapshot of this picture. I'm going to take a snapshot of this object when it is like right there. So given a mass, and I'm not going to put any numbers, a mass M, a length L, and an angle theta of, and this is called a circular pendulum or something, or just of a experiencing uniform circular motion um, on a vertical circular pendulum. Use Newton's laws to determine the speed of the object. Speed v and radius r. So this is the picture. We have the vertical. And theta here, of course, L is distance here. Okay. Now, I do like to put in some vectors representing the velocity and stuff. So this thing is spinning like this, then from this point, I guess so I had made the snapshot here, but let's say I did it here. Forgot how I just, so it's actually here that we're taking the snapshot in that instant in time. So what does this look like? Well, the velocity is into the board at that point. So that guy is V. the acceleration must be toward the center of the circle. Now the circle it's mapping out is kind of in the plane there. I can't really see that, but you might try to draw something like that represents that. That's pretty good. So the radius that one of the things I'm asking for is the radius, which is this distance here. In fact, I don't really even need physics to do that, do I? I can use my geometry. This guy, that distance there is r. So basically, I could create a right triangle with the vertical r, and L is going to be the hypotenuse. If that's theta, then I could just write down the answer to one question, which is that sine of theta is equal to opposite over L. So the opposite R is equal to L sine theta. So that's the answer to the first question in terms of given quantities. And remember that what's given, I only know three things. What's given is M, M theta, and L. Okay. A little bit challenged, my friends. So yeah, let's then apply Newton's law. That's that. Now, the thing is, actually, what are the forces before we apply Newton's law? Well, we've got two forces on the object. We've got gravity, which is acting straight down here, mg, and we've got a tension force. Now, the tension force is, if we draw it from the center of mass of the object, it's got to act back up in the opposite direction, like so. The tension force is back up in this direction. That's 2. Well, I need to define a coordinate direction step 4 in this problem solving process. And I told you to always put a coordinate, set of coordinates so that the acceleration is along one coordinate direction. Now the acceleration is in that direction toward the center of the circle from this vantage point. So it might make sense to make a coordinate system so that I have an axis basically along the horizontal so that I don't have to break my acceleration into any kind of components. So I would choose my coordinate system for this problem to be this thing here. Making X in that direction and Y up here for that point of view. But if that's the case, you see that my tension, I have to resolve it. Mg is along the negative Y direction, but tension, I have to resolve it. Now, you may know that for parallel lines bisecting, the alternate interior angles are the same. And the line, my y-axis is actually parallel to the vertical of my string here. So alternate interior angles, if that's theta, then this is also theta. So I can describe, in fact, that's not the same theta here, is it? So I'm going to call this phi. It's actually complement theta. So let's back Well, it still will be because I can do the bottom triangle. So that's still true actually. But you have to see it from here. Like if I, this makes it makes a box, right? So that's actually a similar triangle to this one, right? The two half. L is the diagonal. So if that's theta, this is also theta. So that equation still applies. I'm still good. Right? That's theta. So this is L and this is R right here. So um uh that's still true. Okay. Well, let's go ahead and do a free body diagram because that's getting pretty messy over there. So if I do my free body, using this as theta, I'm going to have cosine theta basically along the y direction, the positive y-axis. Cosine theta is going to be pointing up like this. So that's going to be a t cosine theta, right? See that? That's the opposite side, so it projects back over here. And this guy, which I can project down here, is the horizontal component, which is sine. So I'm going to have t sine theta along the horizontal direction there. And of course, mg is straight down still. um, yeah. Now, as the thing moves around, there is no acceleration in the y direction. So this is another example where the first law applies to the y direction, and the second law only applies to the x direction. But we have two unknowns, and so those are where our two equations come from. The two unknowns are tension and acceleration. Right, we'll see that from the second law when we apply it. Let's go ahead and apply it actually. Well, let's do the first law first. So doing the y direction, I'll go ahead and put this up here so we remind ourselves that the acceleration is in that direction. Okay. And it's centripetal, so we can put that on too, but we'll do it over here. So in the in the y direction, the net force in the y direction is equal to 0. Why? Because there is no acceleration along the y direction. Now, like I've been teaching you, acceleration, this is centripetal. So now this whole thing is centripetal. Don't have to worry about finding or writing anything about centripetal again. All I need to do at this point is identify what natural forces are on the object. Oh, did I say y direction? So I said y direction. I started right off with this. So let's just go ahead and go for it. So this is actually the x direction. But the only force in that direction is the tension force or the component of tension. So that's what I'm going to put in. So in this case, T sine of theta equals MAC. Well, I don't know MAC, but I know it's equal to V squared over R, so I'll put that in. I guess there's three unknowns. There's T, A, and V. But once I know V, I know A. So, and the third equation is AC is equal to V squared over R. So the three equations are the sum of the force in X, sum of the forces in Y, and the definition of acceleration. And I guess that geometric thing too, because I don't know that. So, because R is also an unknown, but I can write it in terms of L. So four equations, but the geometry is the other equation. So I'm equally determined and I can solve everything. So T sine theta equals M V squared over R. I don't know R, but R is L sine theta, so I'll put that in. So T sine theta is equal to mv squared over L sine theta. Okay. All right. Well, I have to get rid of, I have two unknowns left, T and V. So I haven't used one in my last equation, which is the sum of the forces in the y direction. So the sum of the forces in the y direction equal to 0. So net force in y equals 0. And I've got two forces in the y direction. They are T sine of theta minus mg equals 0. And there you go. That's going to give me my T. And I'm good. So equation 6, T is equal to mg comes over, divided by sine theta. So mg sine of theta. What in the world did I do here? This is, yeah, that's right. So this is wrong. I don't know why I got sine. It's cosine. This, that's what's happening. I think like I said, I'm kind of distracted today. So cosine. So this is T cosine theta. That's along the positive y direction. Equals minus mg. T cosine theta. So this is going to be T is equal to mg divided by the cosine of theta. So that actually gives me one of the things I'm asking you for is the value of the tension force. And that kind of makes sense, right? Because if you look at it, whenever, so this thing is moving like so, right? Whenever the angle goes to 0, the thing is just hanging straight up and down, and cosine of 0 is 1, and so the tension force will be equal to the opposite mg. Cosine of 0, 1 to that, yeah. Yeah. Incidentally, just as a problem I want you to think about, we can talk about it next week or whenever. What is the speed? So you see that as I turn this thing around, the faster I spin it, the larger the angle. What speed must I have in order for the thing to be moving around at a horizontal velocity like this, straight, so that the angle between the vertical and the string is 90 degrees? See if you can apply Newton's law to determine what speed will give you a 90-degree revolution. That's all I want to say about that, and then we'll talk about it. So see if you can do that on your own time. And if I don't say anything about it in class, ask me about it, or if you try to do it and want to ask me if you got it right, let me know. But try to remind me to come back to that, if not today, later, like in the next class, because I want to say something about that and see what result you got on that. But I don't want to say anything else about it because I don't want to give you any hints or anything about what you have to do with that. Anyway, now all we need to do is take equation 7 and plug it back into equation 4. So 7 into 4 will then give us the value for the V. And once we have that, we can plug that back into V squared over R to get A. So this is going to give us putting this guy in here, I'm going to have mg over cosine theta times sine of theta equals mv squared over, now this is L sine theta, that's the R, but that's L sine theta. I got that from over there. L sine theta. Okay. Now the m's will cancel. The sine, so sine over cosine is tangent. I'll write it like that. I like to do it that way. So I have basically g times tangent theta equals v squared over L sine theta. So then solving for v squared equals L times G times tangent theta times sine theta. Yeah. And so now if I take the square root, I have that v is equal to the square root of LG tangent theta sine theta to the 1/2 power. Now I actually didn't ask for v, I asked for a, but let's go ahead and do that. And I don't have to take the square root of that to get a, right? Because by definition, AC is equal to v squared over r, which is equal to L G tangent theta sine theta, but r is L sine theta. So that goes, that goes, that goes, that goes. So AC is equal to G times the tangent of theta. Cool. So certainly that's going to have units of centripetal, of acceleration. So yeah, that is that problem. Now we can do a little bit more with that. I won't do it just yet. We have to wait till we get to oscillations chapter. We can figure out what the period of the oscillation is and the frequency, angular frequency. But I'll leave it at that. This is just an introductory problem here to get that going. Yeah. What do you think about that?
Pretty
Have you
cool.
started to work? Yeah. Mackie, have you started working or seen any of your problems in centripetal in your homework or anything? Have those started to pop up?
Yeah, but I haven't really like done any of them to be honest, like those like specific prompts just because like well, I guess everything. Yeah, exactly.
Yeah. Okay. I know we passed the what time is it? 2:30. Yeah, the break was at 2:30. We passed it. Yeah, because I talked for so much long. Yeah, it's just kind of a off day. I really just think I'm being affected by this war thing. It's got me like all bummed out. So I apologize. I'm not right at the top of my game today. I don't want to overstress you, but I do want to do another one before we go to break. One that they probably are asking you about, or you know, some version of it. I've got a couple of 3 or 4 pet problems that I like to do with centripetal force. So this is another one of my favorites. Uh, it's fall. You might go to a fair somewhere, and you might be sitting on a Ferris wheel. Okay, here's the Ferris wheel, and here's you. You're riding along. Here's your chair, and here you are riding along in the thing. Okay. Now, let's give the thing a radius. Let's say that this thing is a couple stories. So 1, 2, 2.5, 2.25, 2.5, let's say. So 3 stories. Let's say a 3 or 4 story building. We'll say that it's if you have 2.5 meters per story. 4 meters is, or 10 meters is, say, a 4-story building. Let's say 10 meters. That's reasonable, I think. 10-meter radius. Yeah, 10-meter radius. So we'll say that this Ferris wheel R naught is equal to 10.0. You know what? Let's make it 15. 15 meters. 15 meters. And let's say that the period of oscillation is, we don't make it that fast. So 15 meters, I don't know. Let's say that's pretty fast, actually, for a Ferris wheel. But even, so let's say 90 times 9 times 3 is 27. So let's say 270 seconds. Say the period of motion is 270 seconds. That's like 4.5 minutes, I think. Or whatever. 5 minutes, 4 minutes, 4 minutes, 4 minutes. Yeah, 4 minutes. No. A minute is, so 100 goes into that. How many times? No, it's gotta be more than that. So wait a minute. No, 60 seconds. What is it? 60 seconds in a minute? Yeah. My bad. I don't know. Whatever that is. I don't know what that is. It's not a whole number. Oh yeah, what? 4 minutes and 30 seconds. Yeah. Okay. So what am I trying to do? Yeah, so I want to know. So let's say that you are sitting on a scale. You are sitting on a scale right here. Here's the scale. Now, I'm going to put you at 2 positions. Let's call the very bottom of the Ferris wheel position 1 and the very top position 2. Now, obviously, your weight, let's say that your mass is m. So given a Ferris wheel of radius 15 meters, period t, and a person of mass m, maybe 80 kilograms. Mass m equals 80.0 kilograms. Now, obviously, my weight is approximately 800 newtons when I'm just still. But as I go up from position 1, as I go up, what will my weight will appear to be larger than 800 newtons. Just like when you go on an elevator. When I stand on an elevator, my weight is, approximately 800. When the elevator goes up, it looks like I'm heavier. When the elevator goes down, it looks like I'm lighter. And that's called the apparent weight. So if my actual weight is 80 times 9.81, what I want you to figure out is my apparent weight at positions 1 and positions 2 using Newton's laws of motion and the idea of centripetal motion. So, and I remember also your apparent weight, the thing that you're actually, in fact, this is a case, it won't always be, but this is the case where you will have a force. So the centripetal force is always a net, a net force of the forces on the object. But at position 1, I'll give you a hint. One of the forces is acting opposite the direction of centripetal acceleration. according to the archaic people, that should be a centrifugal force. But one, it's not, it's gravity. And gravity is not a centrifugal. Again, there is no such thing as a centrifugal force. But ultimately, it's just the net force on the object is equal to the centripetal force. And the net force is the sum of the natural forces. So what you need to do is at every point, basically, you identify the forces on the object, and there will only be two in those two positions, the weight and the normal force. But those forces change relative to the direction of the acceleration. That's the hint I want to give you. And I'll give you a few. We'll go to break right now, and we'll make this a working break. It'll take a little while. It'll take maybe 15 minutes, 20 minutes. And I'll let you see if you can figure out how to do that. This problem is everywhere. You could even Google it, and some version of it will be there. But so the object is determine the apparent weight, which is basically the normal force, the apparent weight at, and to put in parentheses, the normal force, which implies that the normal force is changing its value. The normal force at positions 1 and position 2 of the person in the seat. Person of mass m equals 80. All right. Let's go to break. I'll let you work on that a little bit. And that's
Professor, you're muted.
Thank you for that. Thank you. So yeah, let's knock this out, and then I think I got time for another one for you. Anybody get a solution, by the way? Share. Okay. Newton's laws are king, always. In the problem-solving technique, once you get to step 4, is sketch and diagram. So this is sketch. How do we diagram it? Always choose an axis and choose what your forces are. So we've got 2 separate points. We have to evaluate those separately, but just like in the problem with the, you know, with the blocks over the tandem blocks, and how I told you to shift the axis over, the acceleration here is always pointing toward the center of the circle, right? So I like to have, again, I like to choose my acceleration so that it's along an axis. And also, if I'm looking at different parts of the problem, the axis can't change, because it doesn't make sense that you're moving along the x direction in one case and moving along the y direction in another if it's the same acceleration, because the same means both magnitude and direction. So the way that I see it is I pin my axis to the object, and the object is moving around. Well, actually, is that true? Can I do that? Definitely if it's moving at a constant speed. Yeah, and you can do that because it's not accelerating relative to the object. It's a little bit shaky there because we haven't talked about something called a inertial frame of reference. An inertial frame of reference means that the axis can't be accelerating. And you might say, well, you know, you're saying the object is accelerating, but if you put the axis to it, why is the axis not accelerating? Well, it's a longer discussion, but I think it's valid because the axis I'm making it relative to a point, the center. And relative to, like, if the axis is here and it's turning like that, it's not accelerating relative to the object. So whether I put it here or shift it down here, so that doing that is the same thing. So that's my argument. It's not accelerating relative to the object. Anyway, yeah. So we, yeah. So then, basically, that's what I'm saying. I'm saying I'm gonna put the axis like this. so that from this point up is positive y, and over to the right is positive x. So when I shift up like this, to the next point, down is positive y, and to the left is positive x. So that the acceleration is pointing along the positive y-axis at all times, which makes sense to me. Okay. So now you analyze the forces. So here I've got mg down. And once that happens, it's pretty simple. It falls out. Mg down, and I've got the normal force up. Remember, there's no centripetal force in there. It is just the natural forces. Here, technically, I've got mg down, right? But now, if there's any pressure at all, which is probably some, the normal force is also pointing down now. Right? The normal force is changing its direction back and forth. Let me make it a different color. So here, normal force. And it may be less than the weight. Okay, so I should like that. Make more sense. And there is more than the weight. Yeah, so it should be a little bit longer than G. Yeah, and so now you just sum the forces at every point. You do Newton's law. So the V is constant, so you're assuming. So it's at position 1, net force at 1 equals mass times the centripetal acceleration. So here I've got, now again, the acceleration is in that direction here and down here. So I always want to write the acceleration so that's positive. At this point, I know the normal force is greater than the weight because the object is going to go up. That's case. Oh, what am I doing? Duh. Sorry, I'm doing something else. The normal force is still up. Sorry. Because he's sitting down, and like he's going around. So up here, he's sitting. Sorry, I'm thinking of a different problem. Just trying to go fast because I'm getting another problem. Sorry. So I should draw it so you see it. So the guy is still sitting. So all right, so the normal force is still in the opposite direction. I was thinking of something like when you do a pail around or something like that, and the water doesn't fall out when it's at the top. In that situation, the normal force would be pointing down. But since the chair is allowed to swivel, the normal force keeps the direction that it has, which is straight up. But it is less than gravity. And how do you know? Because in the next instant, as it moves past the midpoint, the object goes down. In other words, if you just look at the y direction, it's just oscillating back between position 1 and 2. And so when you're at this point, it starts to go up again. So everywhere along this path, normal force is greater now, but decreasing. Now, at that instant, maybe they're equal, and then the next point it goes over. Actually, no. Yeah, the next instant it goes over, it starts to decrease as it goes down. So, so for position 1 here, I've got the normal force minus mg is equal to m v squared over the radius. And again, the two unknowns in that equation are the normal force and the velocity. So I at least need another equation. Where do I get that other equation from? This guy here. So up there, the net force at position 2 is equal to mass times acceleration. Now the acceleration is constant, so v squared and r naught are constant. But now when I put in the values here, I've got now the mass, the weight is greater than the normal force as I go across that critical point. So mg minus, and I'll put this normal force 1 and this normal force 2 because they change. So m, and then v squared is constant over r naught. Yeah. So actually, I got 3 unknowns, so I need a third equation. But the third equation is going to be, I can use the period to get the velocity. I think I did that the other day, that the velocity is equal to distance, in this case, circumference divided by time. So if I have the period, the circumference is 2 pi times r naught. divided by the period. So I can substitute that into this guy, and that's going to give me, yeah. So either one I can find, I guess. I can substitute equation 6 into 5 or 2. Let's do the normal force 1. So normal force 1 is going to be equal to mv squared over r naught plus mg. So putting in v squared here, so n1 is equal to m, and v squared is going to be 4 pi squared. Now the r naught squared will cancel that r naught, so I'm just going to have an r naught there. And I'm going to put in the frequency, right? This is also equal to 2 pi r naught times the frequency. I'm going to do it in terms of frequency. So, because I'm running out of space. But when I square that, that frequency would be squared. So frequency squared, and the R naught has canceled out, and plus mg. So a couple things you see here. You see why the normal force, the apparent weight is larger when you're down at the bottom, because the regular weight is just mg, but you're adding some term to that, some term that's associated with the motion. You can also see why the higher the frequency, the higher this number is. So the more, like if you go faster, he's gonna the apparent weight increases because this number increases. Yeah, and technically the acceleration is a little different too now. The acceleration is equal to the acceleration due to gravity plus some other term over. Let me show you. I'm going to factor out an m over here. So from n1, if I factor out m, I have m is equal to this quantity in parentheses, 4 pi squared r naught times the frequency squared plus mg, or plus g. So that still kind of has the form of Newton's second law. A force equals a mass times acceleration. This term here is going to have units of acceleration. You can see it here. Frequency has units of 1 over second squared. Radius is meters. So this term is meters per second squared. This is unitless. So it's showing you that the acceleration is increasing by this amount. And when f is 0, that's when the thing stops twirling. Then it goes back to being, the weight just goes back to being mg. And when we do this top up here, we're going to get the same thing, except that we're going to be, there will be a negative sign on G. So you'd be subtracting that the absolute value of the weight is going to be different. So you can go through and prove that to yourselves. I'm just going to write it down that N2 is going to be equal to M. Well, actually, I guess I make this negative because I'm saying this is the positive y direction down because I flip the axis over and this is negative. Right? Yeah. Yeah, so let me just go through N2 is here. Yeah. So flipped around. So M that minus mg, and then I'll put the minus on the mg. Yeah, so it's going to be g minus 4 pi squared r naught over f. Yeah. And so now you see why when you're at the top, your weight seems lighter because you're subtracting this term from the acceleration due to gravity into mass. Yeah. Cool. Okay. Let me do a couple more problems while I got you here. Centripetal force. Knock these out real quick. Do a racetrack. Car. Now we're going to look at the top of the racetrack looking down. So here we're at the top, or even coming around a curve. Yeah, so I guess I'd kind of draw a three-dimensional figure here. You got a car. You know what? That's not going to do that. Not hard is like that. So here you have a racetrack, the oval. We're looking from the top down. You got a car. This isn't really straight, but maybe it's a straight track. And then curves. Like that. So when we're going around the curve here, that's the car. If we look at the side view, or maybe here's the velocity is that way. So this is the top view, side view. The car looks like this. And the velocity is coming out of the board. So here's going around like that. And this is the radius here. Or not. Okay. The car is going around like this and here counterclockwise. So, car goes around like this. What keeps it from, so, you know, again, we want to look at relationships between, well, one thing that's oftentimes asked is what is the coefficient of friction? So if you're given the mass, the speed, a constant speed, so given mass, speed v, and radius are not, find coefficient of friction, of static friction, assuming no slipping. Okay, what does that mean? Well, first of all, you got two coefficients of friction. One is kinetic, one is static. We know that if the velocity, if the car is moving along at a constant speed, and at that point it's going, you know, the direction of the velocity is there, there's a static frictional force that is opposite the motion. So kinetic frictional force that's opposite the motion. But, and so, yeah, but if it doesn't slip, then, you know, it tends to want to slip that way, right? When you're going around a curve, you slip out. It's really like you really want to go straight, but then the tires pull you around. So at every point, there's going to be a force perpendicular to the velocity pointing away from the curve that is, a force pointing toward the curve that's keeping you from moving away from the center of the radius. So again, there's nothing pointing away from the center of the curve. That would be a centrifugal force overall, if there's a net force doing that, and there is nothing like that. And there are no other natural forces that would be pointing in that direction, because the only natural force is friction, and it's holding you onto the surface, pointing back toward the center of the circle, keeping you from sliding out unless you do slide. So that's why we're saying no slipping. So if I look at this diagram, I'm going to draw all the forces that are on the object. Basically, I have four forces. I have the normal force up. I have the weight straight down. I have the static frictional force that's pointing toward the center of the circle, keeping it from slipping. So I'm going to call it F static. And I actually have a kinetic frictional force that from this point of view is back into the board, opposite direction of the velocity, which is this vector coming out of the board. I'm just going to put these over here because I'm not going to really need that. The velocity is out of the board at that point, and the kinetic frictional force, Fk, is into the board. So those two I'm not going to really need for this problem. Well, the V I'll need, but the velocity is not a vector, is not a force. So, yeah. Now, in the y direction, I've got the standard. There's no motion or acceleration in the y direction. So from there, I'm going to get the first law, and we'll just see very quickly that the normal force equals the weight. So in the y direction, first law, and then normal force equals mg. Now, I need that because I need it for the static frictional force. Now, in the x direction, the only force in the horizontal direction is the static frictional force. So that, and I know that I'm experiencing uniform circular motion and having centripetal acceleration. So that must mean that, first of all, it's the second law, net force is equal to mass times the centripetal acceleration. And the only force along that direction is the frictional force. So in this case, the frictional force is the sole force that's, associated with the centripetal force. So friction equals mass times v squared over r naught. Okay. Now, friction by definition is equal to mu times n. So I plug that in here. I'm going to have mu s times n is equal to m v squared over r. And from the first law, I have that n is equal to mg. So I put that in. So I have that the static friction, mg equals m v squared over r naught. The m's cancel, and that gives me a formula for the coefficient of static friction in terms of given quantities. That shows me that the coefficient of static friction is equal to, I have to divide through by g, so that's going to be v squared over g times r naught equals the coefficient of static friction. And you can see it's a unitless number, right? So that makes sense. Velocity squared is meters squared per second squared. And acceleration is meters per second squared times meters. So the numerator is also meters squared per second squared. So it cancels out, I have a unitless number. And it shows you that for this problem, then as long as the speed doesn't change, the coefficients are constant. Yeah, cool.
Professor, I had a quick question.
Yes.
Could you go over how static friction, okay, sorry, how the frictions make sense, essentially, is what I'm asking. So, more specifically, how, in the top view, how was the kinetic friction going behind the car? Is that right?
Yeah.
But in the side view, it's going into the board.
Because
or out of the board, I mean.
Well, the side view, I guess I said side view. It's really the front view.
I see.
So I basically, sorry, yeah, I meant side of the, well, yeah. So front view, front of the car. So basically, I take the cars, so this pin is the car. This front view is if I take it and I shift everything up like that, so the car is coming directly toward me. So the velocity is coming towards. So it's like you're standing here looking at the car going around the corner just at that instant. So in the next instant, if I'm looking like this, the car is going to go around like that.
Okay.
Does that make sense?
Yeah, it does.
Yeah. So front view is better. Sorry. Thank you for that. Any other questions about this? We'll go to the next one. Okay, the last one I wanted to do today is this thing, but take it. So, like in regular stock cars, the tracks aren't flat. So in fact, they have the steepest banks in the corners. So in reality, if this were actually, like I'm from South Carolina, we got one of the major five, got the Darlington 500 in South Carolina. I've been a couple of times when I was a kid. So you've got the if you look at the bank, here's the bank, and let's say that this is the center of the track. So the radius basically is here. This is R naught. But you've got the car here. on the embankment at with a plane angle. Now, I guess for now, I want to do, well, I guess you could do frictionless first. Yeah. Probably should do, yeah, that's true. So it gets a little bit gets a little bit complex. Let's do the frictionless first. What I want you to do is what I usually ask for. So here I was asking for the coefficient of friction. Yeah, let's do this. Let's say that well, if the friction is another coefficient of friction. Yeah, let's do this. Let's figure out what the coefficient of friction is in terms of given principles. That will do. But there's other things we can do with this problem. But let's say that we know the velocity. We have a specific velocity. It's going around at a constant velocity v. So again, the same things we know there, but also we got to throw in this angle here. So this is theta. Okay. So given the mass theta, the radius of curvature r naught, and the speed v, specific speed v at that angle, find the coefficient of friction. Okay, so all those look, the same forces are on the thing, right? We got, the velocity is coming out of the board, going around like this, then the kinetic friction is into the board. Gravity is straight down, but now we have to shift our axis like I taught you. We want to do that. So that guys like that goes through. All right. So we've got the weight straight down, mg. We've got the normal force over here, n. There is a so now there's a static. Now the frictional force is up the plane. So there's one. Yeah. Actually, you know what? That's not what we want to do. I messed up because this way we're not having a. We want to make the axis so that there's one. I always told you to put the axis so that one is associated with the acceleration. First thing I should have done. Once I had a brain fart. So, well, I did have one. A is actually pointing in that direction. That's a centripetal acceleration straight, even though the car is banked. Centripetal acceleration is go that way. So I think I want to make my axis like this. I want to make the axis like this. So now the normal force and the frictional force are at angles relative to. This is static friction. Again, kinetic friction is into the board. I don't have to worry about that. It's not going to affect me here. But now, this changes things. mg is straight along the thing. Let me do the free body diagram down here. Jump to that real quick. So now I've got, if this is theta, you can prove to yourself. So you can see it maybe dropping a perpendicular here. But you got to figure that out. I can do it quickly. So if this thing drops straight down, then if this is theta, and that's 90 degrees, then, well, I guess I need a horizontal here too, to clarify. I need a horizontal there, right through that point, make it more clear. That if that's 90 degrees, then this has got to be theta. Sorry, theta's complement. This thing right here is, I'll put it in green. So we know that this is theta's complement. Another way to see it is that you have two parallel lines and cut by this guy, so alternate interior angle. So this is also the complement of theta. But then that's 90 degrees right there. So this has got to be theta. The red is theta. That's theta again. Okay. Which means that this is theta, right? So that angle is same as that angle. So that's also theta right there. And this is 90 degrees. So then this guy is the complement of theta right there. But then that's 90 degrees. So then I have theta again right here. Did I mess up? I did mess up. This is a horizontal, so sorry. This is theta. That's theta right there. But then this is the complement of theta. My bad, I did mess up. But this is the complement of theta, which means that this guy is theta here. It's messy. Let me draw it down here. A bit more of a free body. And you can prove this to yourself. So I'll put it in black like that. So I've got the normal force along this direction, and I've got the frictional force along this direction, F, N. So what I'm saying is that this is theta, and this is theta, and this is mg. Another free body diagram where I break them up. So here I have F cosine theta along this direction, F sine of theta. And then up here, though, I have, that's going to be N cosine of theta there. And then along that direction, N sine theta. And then straight down mg. Yeah, I agree with that. That's what I think. You might have to work back this a little bit slowly for yourself. But now, along the y direction, there is no acceleration. Along the y direction, there is no acceleration. So the net force in the y direction equals 0. And I've got three forces, mg down, F sine and N cosine up. So N cosine theta plus frictional force sine theta minus mg equals 0. So I'm running out of space. So I'm just going to make that equal to mg. But now F is equal to mu S times N. So I'm going to have N cosine theta plus mu S N sine theta equals mg. And you might be tempted to put in that N equals mg or something like that, but it's not true, right? Like you have to do rework every part. In fact, this would tell us what N, if we knew what ms is, us we don't, but if we did, we could solve for N, and N would be equal to mg over cosine theta plus mu S sine theta. As it stands, we got two unknowns, so we have to eliminate N in favor of N, and so we have to kind of work to do that. So for the x direction, we know that there's acceleration in that direction. So in the x direction equals m a c, which is m v squared over r. So we will get, what do we have? Oh, the x direction. So here we have so again, the acceleration is in that direction, AC. So this force in sine theta must be greater than F cosine theta at that point. So what we would write then is that right, n sine of theta minus F cos theta is equal to m v squared over r. But n is mu, F is mu n, so n sine theta minus mu s n cosine theta equals m v squared over r naught.
Wait, Professor, is that an mg cubed on the left side of the board?
No, that's something else there.
Okay.
Yeah. Actually, you know what? I need to look at my notes. I think something's wrong here. I think I might be doing two different problems at once. Oh, yeah, I am doing it. I said it was frictionless, didn't I? I said it was frictionless. I wanted to do that first, and then I started my. Okay, sorry. Yeah, we have to know the coefficient of friction to do this. That yeah, we have to. But if it's friction, yeah, sorry. I would have to. What I'm doing, you would have to know the coefficient of friction. So I'm doing two things at once in my head. I'm so sorry. If it's frictionless, there is no frictional force. Well, and we want to. What? What am I trying to do? Angle, okay, tangent. But I kind of want to show that because we showed that when we did this before, that mu, when you're on an angle, is only a function of the angle. And I wanted to try to show that again. But difficulty doing that. Let's try this, or maybe not. Maybe I can get to it. So here, if I factor out the n, I should be able. Maybe I still can get to it. So here I'm going to have n quantity sine of theta minus mu s cosine theta quantity equals m v squared over r naught. And over here, I'm going to have n quantity cosine of theta plus mu s sine theta equals mg. So n basically equals mg divided by cosine of theta plus mu s sine of theta. Okay. That does make sense to me because you can see that when theta is 0, that whole term goes to 0, cosine of 0 is 1, and n equals mg. So that works out. So if I substitute that over here, then I'm going to have I'm going to have mg, basically this stuff here, sine of theta minus mu s cos theta, divided by cos theta plus mu s sine theta equals m v squared over r naught. Now the m's will cancel. Yeah, I'm going to have difficulty uncoupling that mu s out of that if that's what I was trying to go for. But I guess you can do it though, right? Because, yeah, let's go ahead and see if we can do work reality. Since I asked you, go ahead and see if we can do it. So I'm going to multiply through by g and divide by g and multiply this term. So I'm going to have sine of theta minus mu s cosine of theta equals v squared over g times r naught, but then times all of this, which is going to be cosine of theta plus mu s sine of theta. Okay. Now the mu s is on these two terms, so I got to get those together, which I can now. I multiply this by this term and just take this guy over. And then multiply this by this term and take that over here. I'm going to do a couple steps at once. If I don't make a mistake, I'll let you can follow it through. When this term comes over, it'll be minus. Sine theta is still there. So I'm going to have sine theta, and then this is going to be minus v squared over g r naught times cosine of theta. That's this thing multiplied right over here. Now I'm going to take this guy over here, and I still have to multiply this term by the second. So I'm going to have, so this comes over, it's going to be equals plus mu s cosine theta, and this guy times this, which is plus mu s is there, it's right here, and v squared over g r naught times sine of theta. Now I'm home free. This is the home stretch. I'm going to factor out a mu s from this side, okay? So I'm going to have mu s times quantity, these two things. So cosine of theta plus the mu s is factored out, v squared over g r naught, v squared over g r naught times sine of theta. Over here, I still got all that crap. So sine of theta minus v squared over g r naught times cosine of theta. And now I'm done. So mu s is equal to this thing, sine of theta minus v squared over g r naught cosine of theta divided by this thing, which is going to be cosine of theta plus v squared over g r naught sine of theta. Now, that might actually look a little crazy, but I believe that's right. I don't think I've ever done this problem before. I thought I had, but I don't think I have. But just at first glance, that looks right. Because remember when I had, like, what if this car is just sitting on the embankment and it's not moving? At what angle should it be? Where, it would have to be whatever the angle it is. We did a problem like that where we said we sit something on a ledge and it's not moving, but if it's at a point where it doesn't slip, what is mu s? And what we showed is that mu s, the coefficient of friction, is only dependent upon, I think I did that. I hope I did that for you. If not, we'll do it. We can do some more problems. We'll continue doing problems next week. I might be confusing this with my summer class. Maybe I didn't do this with you yet, because we just talked about friction I'm kind of drawing the blank. I don't, was that Monday or was that last Wednesday? I don't remember. But this, so I thought we had done that already, because when you do a problem like that, you see that mu(s) is only dependent upon the tangent of the angle. That's an easy problem to do, where you set up, it's just the normal force, gravity, and the frictional force. If you're right at the critical point where it doesn't, I think I did that, where it doesn't slip, you can show that that mu(s) is equal to tangent of theta. And so you can see that this is going to reduce to that whenever the velocity is zero. The velocity is zero, that term is out, zero, that term is out. So you just have sine over cosine, which is tangent. So that makes sense to me. That's a correct solution, because it has to reduce back to the simplest thing. Now, we also showed that I don't know what I was going to say. Yeah, I don't know what I was going to say. But that's the solution. It's kind of, and it's all in terms of given quantities, right? Because I've given you what we knew was the mass theta of v squared and r naught. So you could figure out what the coefficient of friction is just by plugging in now. So that kind of got to be a lot of algebra, but basically it's just, and I went fast, so I hope I didn't confuse you, but it's really just you with the same procedures over and over again, where you establish coordinate axes, you put in your forces, you sum the forces, and you're going to get a set of equations that you have to solve. And the idea is to be able to apply Newton's laws correctly, depending on the type of motion that it is and the forces that you have. You then may have to use some ancillary kind of definitions, like definition of friction or definition of centripetal force, centripetal acceleration, whatever, to put in to help with that, to complete, to be equally determined. But the basis, the fundamental basis, is being able to apply Newton's laws fundamentally correct in order to get a accurate set of equations, system of equations that you must solve simultaneously. So I'm going to let you go ahead and, continue to start working on some of these problems. Continue to work on the problems, and maybe you can address some of the centripetal force stuff as well. Like I said, I'm going to open up the test because people may want to start, but it won't be due until Tuesday. So you still can work on homework and stuff. And on Monday, you can ask me questions that you might have, as you take the weekend to study and prepare yourself. You don't have to take the test this weekend. Again, it'll be like you have to take it within, I think, 3 hours, 180 minutes. But you can take it at any time during the time when it's open, which would be, I guess, Friday to Tuesday night that you want. So you can wait till Tuesday to take it if you want. And so you can study over the weekend and ask me some questions. But yeah, there's plenty of other, I've got like lots of problems. Maybe I did post some stuff last weekend for separation of variables. And I'll probably post some more stuff as well, along with that and other things. And that will help with your studying and that sort of thing. Post some other stuff about drag. That should help kind of fill out the lectures. Okay, any questions? Sorry, I took you over 2 minutes. Any questions, problems, troubles, gripes, anything? Hello? How you feeling? Anybody there?
Yeah, I'm here.
Hey, Arthur, how you doing?
I'm good. You?
Good. Good. So any questions about anything?
No.
I think
To be honest.
I'm gonna get to your email today, by the way. I don't think I answered it, but
Oh
I
yeah,
saw
no,
it
I
there.
was just asking if we had a free day on Monday, but no, we don't.
Oh, what's Monday? Is there a holiday on Monday?
No, it was like previous Monday. It was Columbus Day.
Oh, Columbus Day. No, we don't take Columbus Day. I think they don't do that because I think don't we get a day during the fall? Isn't there a fall break or something? I don't know, but no, we don't get Columbus Day off. But there's some reason why that I forgot. I used to get Labor Day off. Yeah, I don't know, but no. All right, cool. Some people might have taken it off because you can always look at the lectures. I mean, it's hard to tell because only about 15% of the people come to class regularly. All right, well, that's it. I'll let you go. I've kept you over already. Have a great weekend. Be safe, and I will see you on Monday. Keep working consistently because we have to kind of pick up the pace a little bit, but we got to stay at this pace for the next several, basically for the rest of the semester. Please don't get behind.
Thank you,
All right.
Professor. Have a good day.
Okay.
Thank you,
Thank you.
Professor.
Ask Brian, you got a question? No questions. Thank you. Also need to find your message, but no worries. It's all right. It's all good. Yeah. Thank you so much. And have a great. I want to post other stuff about the drag stuff too. I'm working on it. So it'll be, I think maybe I'll break them up into separate lectures. So you got the one on basically that's about separation of variables. Then I use that to derive the equations of motion. And I do it twice. I do it for just a general acceleration, and then I did it for free fall motion. But the next thing is to go back in, introduce drag, slow and fast drag, and then use separation of variables to derive equations of motion for that as well. So I'll do it over this post. I've already written out the problem, but I'll do it over here. So you can take a look at those at your leisure. All right.
Okay, thank you.
All right. Thank you.
Bye.
Bye bye.